Hey YouTube, it's Sebastian KF5 OBS, and this is gonna be the second video for my video blog. As promised, we're gonna tear down a C-Band LNB, but before we do that, let's talk a little bit about the feedback you gave me. It was generally good feedback, and there was a little bit on criticism on the audio and the lighting setup. I totally agree with the lighting setup. I was just using cheap construction lights, and they absolutely did a horrible job at what I was using them for, so I bought some more professional lights. That they are still kind of amateur, but hey, this is what this is after all. So I got a key light over here, I got a fill light there, and I got a background light behind me, and the color temperature is supposed to be daylight, so I hope all this here is looking much better than it did in the previous video. Now, the other criticism was on audio, and I don't have a solution for that yet. My camera doesn't have a microphone input, so I'm probably going to end up recording audio individually in one of my further videos and sync that up before I actually edit the video. It's probably going to be the best and the cheapest route to go. Okay, now to our C-Band LNB. What is an LNB? What is the C-Band? And what is all this stuff? Okay, so LNB stands for low noise block, a generic term that doesn't really tell you anything about what this thing does. It only tells you something about its noise performance. And C-band is a frequency band around 4 GHz. Where is this used? In satellite reception, TV, broadcast satellites to be precise. C-band is, I think, dying out, but here in the United States it's still used by broadcast companies. And what this tiny little thing basically does, the signal from the satellite, focused by the satellite dish, goes in here, and it's being translated down to a much lower frequency and comes out of this F connector. We're having a signal at about 4 GHz coming in here directly from the satellite. That's being translated to the L band, which is around 1 to 2 GHz, coming out of here. And we do that because if we would put a 4 GHz signal through a coax cable, we would have much higher losses than if we do it at a lower frequency. And additionally, if we kind of agree on one intermediate frequency on every satellite receiver, we can use different local oscillator frequencies and use the same receivers for different satellites and different frequency bands. But let's not get carried away with that. Now, this particular one is a professional one that's used at broadcast stations and has this waveguide mount right here. And if you look inside, you will spot a little tiny thing there in that corner, and I hope it focuses kind of okay on that. The camera is probably going haywire with the automatic white balance now, but that thing is coupling in the RF coming from the satellite, focused by the satellite dish, into the circuitry. And what the circuitry does and what it looks like, we're going to look at right now. Alright, that's the first LNB we're going to tear down. And you may have already seen a teardown in my actual text blog. If you haven't and you feel like reading it, the description is going to be down below this video. Now let's look at the specs for a minute here. It says the input frequency range is 3.4 to 4.2 GHz. The local oscillator frequency is 5.15 GHz. The stability is rated as plus minus 250 kHz. Now, you notice that the local oscillator frequency is higher than the input frequency, and it's also higher than the output frequency. It doesn't give you the output frequency here, but it's generally with satellite receivers, it's in the L band, which is around 1 GHz. And I think the actual frequency range is somewhere between 900 and something megahertz up to barely 2 gigahertz, like 2.1 gigahertz. But every time the LO frequency is higher than all the other frequencies involved, you're going to have a spectrum inversion. And I'm going to mention what that does once we get into this box. Okay, let's open it up. I already removed the screws, and there it is. What do we see? Almost nothing. Because we have a bunch of shields. Got a shield here, got a shield right here. This one is actually the tuning mechanism and shield for the dielectric oscillator, but we're going to look at that in a minute. First, let's look at everything that's over here. And there we go, that's looking much better. Okay, this solder point right here goes to that little element that I showed you earlier and is coupling in our 4 GHz signal into those 3 transistors here. They are probably some special field effect transistors. They could be MMICs, but I doubt it, because it seems like there's a bias voltage, and MMICs usually don't have an external bias. They have a supply voltage and that's it. They have an internal bias, so I assume that they are probably PHEMT field effect transistors. But anyway, there's 3 of them, and they are boosting up the very weak input signal a lot. Up here you'll have some voltage stabilization and some bias point adjustments for those 3 transistors. And then the amplified signal goes into this funny construct. What's that? That is actually 2 bandpass filters in a row. To be precise, they're called hairpin filters. Hairpin because those traces are so thin, kind of like hair. I guess that's where that's coming from. Anyway, they're bandpass filters, and you can already see one advantage of high frequency or really high frequency circuit designs. Many things get so much more compact. For instance, over here, this is your RF choke. You know, with lower frequencies you'd actually need quite a bit of inductance to keep RF out of your supply rail, but because we're having such high frequencies, you can get away with moderately small inductance, and you can print that on your circuit board. You don't need to actually put anything in place there. Same with the filter. You can just, you know, it's really tiny, and you don't really do any math behind that. When you design one of those, you use software that does the trick for you. I mean, if you absolutely want to, you can sit down and do the math with the formulas and stuff, but nobody does that. Really, nowhere does anybody really do that, unless they want to do it for fun or their professor tells them to do so. Okay, so the amplified and filtered 4 GHz signal goes into this funny thing, and what that is I'll tell you in a second. So, that's where the 4 GHz signal goes in on one side, and there's something coming out from this side and going into the same thing. As I already said, under here is the dielectric resonator oscillator, and what that looks like I will show you as soon as I get the screws out of here. Alright, here we go. And let's get that one screw out of there. Here we go. Alright, inside this purplish thingy up here, you're seeing this white little pellet on the bottom, and that is your dielectric resonator. And there's a transistor right here, that's the oscillator transistor. And a dielectric resonator is, well, of course resonant on a certain frequency, but it's not electrically resonant. This works with magnetic fields. It's called permittivity, and this entire oscillator setup is very similar to a standard Pierce crystal oscillator, though. One of those wings up here will be connected to the collector of the transistor, and the other side to the base. This here is probably the collector, and this one will be the base, because you usually couple the signal out at the collector with a Pierce oscillator, so that's probably what it is. And I'm pretty sure if you'd rip out this dielectric resonator and would put a crystal across those 2 pins, it would probably start resonating on that frequency. But it's magnetically coupling this dielectric resonator in here, and that's the reason why we need to shield it. Because, here's our shield. Hang on, let me get rid of the screws. Any disturbance in the magnetic field that's caused by, well, anything, changes the frequency directly. And this is why you can tune this entire thing with this screw up here. If you turn the screw goes in more or out, depending on what direction you turn the screw. And by that you're changing the way the magnetic fields behave in here, and therefore the frequency directly. And some amateur radio operators sometimes modify these LNBs to transmit. They are basically doing the same thing, just the other way around, and then they're changing this frequency by a very simple means, by just putting, for instance, a drop of glue on top of it. Pretty much anything you can think of that's changing the properties of this device over here, this little white thing, will alter the frequency directly. Now, okay, we're coming out of here, and this is a strip line, obviously, a matched impedance strip line, and this here will be an attenuator. It's probably just to make sure that the load of this thingy here isn't too big on the oscillator, or maybe the level is too high, I don't know, but it's probably they want to keep the load to a minimum. Now this thingy here is what's called a hybrid coupler. It couples this signal and this signal together to this point, but isolates those two ports from each other, so there's no direct feedback from this side to the oscillator and the other way around, but they are combined over here. They are only added, not multiplied to this point. They're only added, so over here you're having both this signal, the 4 GHz signal, and the 5.15 GHz local oscillator signal together. Now we want to mix them though. So that's what this tiny thingy here is for. This is a dual Schottky diode, which introduces a nonlinearity, and we know every time we introduce a nonlinearity and we distort signals, those signals starting to multiply, and that's what's happening here. Now, as said earlier, every time the local oscillator frequency is higher than our IF frequency and the input frequency, we're going to have a spectrum inversion. And if you think about this for a moment, we are subtracting whatever comes in here from our 5.15 GHz LO frequency. And that means if I increase the signal coming in here, our output will decrease, and the other way around. And that essentially inverts your entire spectrum. That means if you have a 6 MHz wide video signal in the middle of our passband here, the bottom edge of the spectrum, the top edge, is going to be inverted at the output in regards to how it has been transmitted. And that's something you need to be aware of. Most satellite receivers have the option to switch between video inversion and video not inverted, and that's a very handy feature, and it is something that particularly amateur radio operators have to deal with when they get into amateur television. And sometimes people have a very nice working setup, except their video looks kind of funny, and that's all it is, that they didn't watch this inversion thing. Now anyway, now we got the mixed signal up here. It's going out in this direction, and it's being amplified a little bit more, and goes out through this connector here, which is a standard F connector. You see up here, the F connector also carries our positive supply rail in the center, and over this choke up here, the power is being extracted, and over here stabilized and fed through the circuitry where we need it. I mean, this here is passive, it doesn't need any power, but you see some power going over here, and we're seeing some power coming in here for the oscillator. That's what this is doing. That's pretty much everything that's inside an LNB. There's not much more magic to it. And just if you look at this, you should be able to tell that actually it's pretty easy to design stuff in the gigahertz range. Of course, I'm sure many of you have never seen a hairpin filter before, or a hybrid coupler, or any of those. But as I said before, there's mostly computer-aided design software that helps you designing these sort of things. A software, for instance, used to determine the track width for certain impedance could be AppCat. AppCat is a free software, and I'll throw the link in the description if you want to have a look at it. And as I said, there's not much to it, and all you gotta do is convert the numbers it's given you into a printed circuit layout, and you're doing that already. When you're designing any printed circuit boards, you look in the data sheets, look at case styles, what's the spacing between pins, and you're implementing that in your design. And it's very similar here. All you're doing is transferring dimensions in there. I mean, if you want to understand what's behind it, that's great, and I highly encourage you to do so. But technically, you could just copy stuff and put it on your board, and it'll work. It's really easy. One thing is, it's all small, and the higher you get in frequency, you want to be surface mount. Something in the gigahertz range, you almost always want to be surface mount. But in my opinion, surface mount has many advantages over standard through-hole parts anyway. For instance, my box full of surface mount parts is a tiny shoebox, and I got countless parts in there. And my boxes for through-hole parts, it's several huge boxes, and they about contain the exact same parts, just surface mount is so much smaller and less expensive too. Okay, now I said that this frequency stability thing isn't all too bad for analog signals. An analog signal is about 6 megahertz wide, and it doesn't matter if you're 250 kilohertz, too high or too low. Most receivers have automatic frequency control anyway, so it doesn't matter. But digital signals need a lot more stability. And I got another LNB over here. Okay, let me put something under it. This here is obviously a little bit more stable. It says the stability is plus minus 5 kilohertz. And you cannot achieve a stability like that with a dielectric resonator and an oscillator built around it. So let's open this one up. Let's see how a PLL stabilized LNB looks like. Oh, there it goes. Okay, different circuit design quite obviously, but the exact same thing than we have seen in the other LNB. Over here is our input stage. Our 4 gigahertz signal comes in, gets amplified by 3 transistors of some sort. Up here is voltage stabilization, both supply voltage and bias voltage. We're going here through a coupling capacitor into hairpin filters. Over here is the hybrid coupler, and we're having something to introduce a nonlinearity again. Over here we have power extraction, power stabilization. We have an L-band amplifier going out, the exact same thing. The only thing that's missing over here is the oscillator. We've got a pin coming in here, feeding us our local oscillator signal. Now let's look at the oscillator itself. It's actually on the other side of this LNB. And here it is. Alright. First thing that catches our eye is this temperature compensated oscillator. It's around 10 megahertz, and it's being multiplied by a factor of 512. To be precise, it should be around 10.058 something megahertz. And if you multiply this by 512, you get in 5.15 gigahertz again. And over here we have our PLL, and this right here, that's our voltage controlled oscillator. And you see right here, this is where our RF path starts. And you got RF coming out, going through this way. It's obviously being amplified. I would almost bet this here is an MMIC, and goes out this way. Over here we got a filter again, making sure that only our wanted 5.15 gigahertz signal is passing through. And that's it. It's again a very simple circuit. There's not much to it at all. And you could probably design something like this at home as well. And that's exactly what I wanted to show. I didn't want to talk much about RF circuitry yet, just to show you that lots of this magic witchcraft stuff isn't so much of magic witchcraft at all. It is rather simple, and there's probably a bunch of new things that you've never seen before, like these kind of filters, and the hairpin filters on the other side. But those are all things we're going to talk about, that I'm going to cover in this blog, and you'll soon know how to design and how to use them. Alright, I hope you enjoyed this little video. If you did so, please give me a thumbs up, and make sure you subscribe if you haven't already. And other than that, give me your feedback. I would like to know how you liked it, what you didn't like about it. And oh yeah, one thing I'd like to know, the C-band itself isn't used much anymore around the world. I know that, but I don't know in which countries it's still being used. I think it's still used in Russia, and in the United States it's used a lot for a broadcast station. They get their feeds for pre-recorded programming, and sometimes commercials are fed through the C-band satellites. So if you know anything about the C-band, how it's being used in your country, or when it has been considered obsolete, post below. That'd be interesting for me to know where it's still being used and where it isn't. I know in Europe I've never really seen a C-band dish. They've always been KU, I think, at least for as long as I can think, and here in the States you're still seeing C-band satellite dishes everywhere. Broadcast stations usually have a huge amount of those for the reasons mentioned before. Alright, so give me some feedback on that, and thanks for watching, and see you again soon.